Alright, now let's see. This thing won't move for me, but I'm going to kind of see if I can do that. Alright, we'll just leave it in this kind of offset frame here, and I ended up that last video putting this function in, trying to use all kinds of different tools, and I didn't quite show it to you, and the reason I didn't show it to you because I didn't have my scale set on sketchpad. So you'll realize here on sketchpad, sometimes you can get so far down the pike that you can't see these two little dots here, and these are the two dots is the way you control where your coordinate system comes out on the graph. And so to change the scale, you kind of just grab them, make them smaller and bigger. So what I've done is I made them small enough now that you can start to see what that function looks like that I drafted out, and I just kind of made it up on the fly, just letting you know that the fourth integral of the load curve is this fourth order curve, and that's what typically the shape, deflection shape will be, look something like that. It will be a fourth order. You'll see them as you look at tables for lookups, but you really want to start in, like many things in structures, in terms of just guessing and doing a side calculation. That's part of your triangulation here. So I just made a bad guess here, but it didn't turn out too bad, because right now, at least for a certain domain of that function, you get something that looks somewhat similar to this function here. Now, if you go back to analytic geometry, you will know that if you have something that's got a fourth order, it will have three relatives or maximums. It's 1 minus. And the easiest way to think about that in terms of a trend is that a line has no relative maximum or minimum. A parabola has 2. And as you go up from there, a parabola has 1, I'm sorry, so it's 1 minus the highest order of the function. And if you notice here, this has relative maximums and minimums at a point there, a point there, and a point there. And so you get a little bit of that same, not exactly the shape that I sketched out, but we get the concept of what, how shapes are almost always mathematical functions, or they can be approximated to be. You have a lot of something called empirical numbers in engineering, or empirical relationships, and that's kind of where we force an equation or a set of equations to a set of data by regression. But in this case, we think about the steps of solving basic structural problems, and really what we want to start to do is add a side step to that, and that would be to sketch the shape that you think, and you're not going to be certain of it sometimes. That might not be too intuitive. You think that one or several of the forces will cause, the deformation it will cause. And eventually the rule of superposition will let you know that the incremental deflection or shear or moment caused by any single force or set of forces is additive. And that's an important concept in lots and lots of engineering, in circuits and lots of different things. So that's the rule of superposition. So just here, I'll finish this up and make it short. That'll make that a 15-minute. And a lot of this is just demo of software here, which some will use, some will not. My sense is that the smoothboard, depending on the computer, and may or may not be the interface to use this bamboo tablet. They're available for $69. The prices will come down. Tablet computing is here, along with those cool black helicopters that you can fly around the room. Probably at about $500 that are coming out of Vegas. So we can just show you, as long as I'm going to finish out 5 minutes here. So you got a circle here. I can actually now not only put functions in this way and graph them, I can graph functions. And now that circle there, if you notice, is a child of this function. So when I grab now that circle here, and now I do display animate point, since it locked this point down here of the circle, this was locked. If you notice here, this point is traveling along the function. So you have some more parametric, and that's going to get pretty huge pretty fast. Let's see if I can make that. There it goes. You notice there, because I'm changing the scale, and some of that locking things down, I think you're going to see in this program, might not be locked to coordinate system, might be locked to the page. So let's see. Yeah, if you think about it, it's actually locking that that's news to me. It's locking that point over here to actually not to the coordinate, to a point on the screen. So you're going to see there's, as we get going on this software or this, our graph or anything like that in a course or in a math course, you're going to see you need to grab the idiosyncrasies of the software and discover them as you go. The book, the literature on this is not so great, but it's not so bad. All right, there's the function x to the fourth function there. This is a circle function. Let's see how far it's gotten going up that. Oh, it's getting pretty big there. And what you're doing is you are at this point, I'm fixing one point on the circle and changing the center. Thanks for listening.